So again, I've talked about this in our last part of this video, but remember where concavity changes is called a point of inflection. So very much like our critical numbers or critical values are places where a min or max could occur, we find the possible points of inflection, but we can't call it a point of inflection unless concavity actually changes. So I've given you 3 pictures where concavity does change and what that might look like. If you find a possible point of inflection where concavity doesn't change, we don't call it a point of inflection. I'm not going to spend a ton of time on this video because I feel like in the last video we really talked about this a lot. But again, the definition is essentially where concavity changes from up to down or down to up. So how do we determine where that is? Well, just as we did in the last video, we determine where f double prime of x is 0 or where f double prime of x does not exist. So the same thing we did for relative extrema, critical values. This is a possible point of inflection, and then we determine if concavity actually changes, we call it a point of inflection. So this is very similar to a question that we've already done, where we did determine concavity, intervals of concavity. Here we're talking specifically about what are the points of inflection. So points of inflection would be any place where concavity changes. So what I've done is I've started with my original function. I've determined both the first and second derivative, and the second derivative was 12x squared minus 24x. I decided to set that equal to 0 to find the intervals. So pretty easy to factor this guy, 12x times x minus 2, which gives me 0, 2. Defined everywhere, which means there is no point at which my second derivative is undefined. So I only have those 2 possible points of inflection at x equals 0 and x equals 2. I'm making my table as I did before, and I'm plugging it back into f double prime to find positive, which means concave up, or negative, which means concave down. On this one, I'm asked to determine both points of inflection and concavity. So I would start by talking about it being concave up from negative infinity to 0 and from 2 to infinity, and concave down from 0 to 2. And then the points of inflection are at these boundary points. So at 0 and at 2, or notice I can find more specifically those points. Now where did those more specifically come from? I would have had to take 0 and plug it back in up here, and 2 and plug it back in up here, and that's where I found 0, 0, and 2, 16. Typically, I would end right here. I wouldn't find the points of inflection unless I'm actually curve sketching, which is coming in our next section. So here's one for you to try. Again, I want you to do both points of inflection and concavity. When you're ready, press play to see how you did. So again, the first thing that you should do is to find the first and second derivative, which again, this one was pretty straightforward because it's a polynomial. I didn't write that, but I should have written this is continuous and differentiable over the entire domain. Therefore, I can find the first and second derivative. So my second derivative is 12x minus 6. That gives me just one 0, which is just one possible point of inflection, which is at 1/2. So notice I've broken my interval into just 2 parts, separated at the 1/2 mark. Plugged those back into f double prime of 0 to find concave down and concave up. And then again, to discuss concavity, I would just give those 2 intervals, and then I would talk about the fact that I have a point of inflection at x equals 1/2. And if I wanted to be more specific, I could take 1/2 and plug it back up here to get 1/2 comma negative 3/2.